throw an apple into the air. Newton says it will fall. If an object is launched upward near the Earth's surface, classical physics teaches us that it will slow down, reverse its motion, and return downward. This behavior is stable, repeatable, and predictable. But what would happen if that apple did not fall? Newton's laws and their extensions work well for macroscopic objects and provide unique solutions when the initial conditions are known. Quantum mechanics emerges when studying microscopic systems, such as electrons or photons, and introduces a different mathematical structure in which the state of the system is not described by definite values, but by a wave function encoding probabilities. Before entering this fascinating world, remember to support our community by subscribing to the channel and leaving a comment if you are interested in this type of content. On this channel, we explore the mind, the world, and human understanding. Richard Feynman, Nobel laureate in physics, stated that no one truly understands quantum mechanics. Even Einstein, despite his philosophical reservations, declared, "God does not play dice with the universe." Yet, unlike purely theoretical paradoxes, quantum paradoxes are embedded in the very fabric of the universe, and each appears more striking than the previous one. At the center of this remarkable universe lies the principle of superposition. A particle can simultaneously exist in multiple states until the moment of observation. This does not mean its state is undefined. The particle indeed occupies all these states at once, and only the act of observation forces it to collapse into a defined reality. The issue arises when measurement is considered. Schrödinger's equation describes a continuous deterministic evolution of the wave function, but the act of measurement yields a single outcome. Erwin Schrödinger formulated a thought experiment to illustrate the difficulty of directly applying quantum formalism to everyday objects. In a closed box, there is a cat, a mechanism linked to the decay of a radioactive atom, and a vial of poison. The decay is a quantum event, and before measurement, the atom is described as both decayed and not decayed. If this description is extended to the entire system, the state of the cat is also undefined. Schrödinger's aim was not to suggest that a real cat is physically in two states, but to highlight that the direct interpretation of superposition leads to results incompatible with macroscopic experience. Superposition is closely connected to the phenomenon of entanglement. Two particles created in the same quantum state can become correlated so that measuring one immediately determines a property of the other, even if the particles are separated by large distances. This instantaneous correlation is incompatible with the classical concept of locality, according to which no influence can propagate faster than light. Einstein called this behavior spooky action at a distance because it appears to violate the principle that effects must have local causes. To explain entangled correlations without violating locality, Einstein, Podolsky, and Rosen hypothesized the existence of local hidden variables, unobservable parameters that would determine measurement outcomes from the outset. However, this hypothesis remained experimentally unverified until John Bell formulated a mathematical inequality capable of distinguishing the predictions of quantum mechanics from those of theories with local hidden variables. Repeated experiments confirmed that correlations between entangled particles exceed the limits imposed by Bell's inequality, demonstrating that the quantum world is inherently non-local. Another key experiment is the double-slit experiment. If single photons are sent toward two parallel slits and no measurement is made to determine which path each photon takes, an interference pattern appears on the screen, characteristic of wave-like behavior. However, if a detector is introduced to determine the path, the interference disappears, and the photons behave as particles. This demonstrates that the act of measurement not only reveals an outcome, but directly influences the observed result. The quantum eraser paradox extends this principle. Entangled pairs of photons allow for retroactive alteration of information availability about the path of one photon, changing the observed pattern in its partner. When the information is erased, the interference pattern reappears, showing that the temporal order of measurement does not coincide with the classical perception of past and present. The statistical structure of the data changes depending on the presence or absence of observable information without violating quantum causality. Measurement and superposition also raise Wigner's friend paradox. An observer inside a laboratory measures a quantum system and records a result, while an external observer describes the entire laboratory as a system in superposition. Both descriptions are consistent within the formalism, but they are incompatible if a single objective collapse is assumed, demonstrating that no clear boundary exists between the macroscopic and microscopic worlds. The quantum Zeno effect illustrates a practical application of the role of measurement. Frequent observations can slow down or prevent the evolution of a quantum state, for instance, delaying the decay of an atom. This property is used to stabilize fragile quantum systems, such as ones used in quantum computers. Other applications include interaction-free measurement, where a sensitive object can be detected through photon interference without direct contact. The absence of interaction produces information about the object's presence by altering the interference pattern. The contrast between relativity and quantum mechanics becomes evident in black holes. According to relativity, a black hole is characterized only by mass, charge, and angular momentum, and matter that falls into it seems to lose information. Quantum mechanics, however, imposes the conservation of information. Hawking radiation demonstrates that black hole evaporation involves the dispersion of energy, yet the fate of the information remains an open problem, indicating the need for a consistent theory of quantum gravity. The many worlds interpretation proposes that every measurement corresponds to a branching of the universe in which all possible outcomes occur in separate, non-communicating branches. Applied to extreme experiments, this interpretation describes the subjective persistence of observation only in branches compatible with survival, without contradicting the mathematical formalism of quantum mechanics. These phenomena show that the quantum world does not contradict its internal laws, but requires a rejection of classical intuitions about reality, locality, and measurement. The formalism produces precise experimental predictions and operational technologies, while leaving profound interpretive questions open. For additional content with detailed and structured analysis of quantum physics and its implications, the channel provides similar material. Subscribing allows systematic access. Thank you for watching, and if you do not want to miss future videos, subscribe to our channel.